A high-voltage, direct-current electric power transmission system uses direct current for the bulk transmission of electrical power, in contrast with the more common alternating current systems. For long-distance transmission, HVDC systems may be less expensive and suffer lower electrical losses. For underwater power cables, HVDC avoids the heavy currents required to charge and discharge the cable capacitance each cycle. For shorter distances, the higher cost of DC conversion equipment compared to an AC system may still be justified, due to other benefits of direct current links. HVDC allows power transmission between unsynchronized AC transmission systems. Since the power flow through an HVDC link can be controlled independently of the phase angle between source and load, it can stabilize a network against disturbances due to rapid changes in power. HVDC also allows transfer of power between grid systems running at different frequencies, such as 50 Hz and 60 Hz. This improves the stability and economy of each grid by allowing exchange of power between incompatible networks. The modern form of HVDC transmission uses technology developed extensively in the 1930s in Sweden and in Germany. Early commercial installations included one in the Soviet Union in 1951 between Moscow and Kashira, and a 100 kV, 20 MW system between Gotland and mainland Sweden in 1954. The longest HVDC link in the world is the Rio Madeira link in Brazil, which consists of two bipoles of plus or minus 600 kV, 3,150 MW each, connecting Porto Velho in the state of Rondônia to the São Paulo area. The length of the DC line is 2,375 kilometers. High-voltage transmission. High voltage is used for electric power transmission to reduce the energy lost in the resistance of the wires. For a given quantity of power transmitted, doubling the voltage will deliver the same power at only half the current, since the power lost as heat in the wires is proportional to the square of the current for a given conductor size, but does not depend on the voltage. Doubling the voltage reduces the line losses per unit of electrical power delivered by a factor of 4. While power lost in transmission can also be reduced by increasing the conductor size. Larger conductors are heavier and more expensive. High voltage cannot readily be used for lighting motors, so transmission level voltages must be reduced for end-use equipment. Transformers are used to change the voltage levels in alternating current transmission circuits, because transformers made voltage changes practical, and AC generators were more efficient than those using DC. AC became dominant after the introduction of practical systems of distribution in Europe in 1891 and the conclusion in 1892 of the War of Currents, a competition being fought on many fronts in the U.S. between the DC system of Thomas Edison and the AC system of George Westinghouse. Practical conversion of power between AC and DC became possible with the development of power electronics devices such as Mercury Arc Valves and, starting in the 1970s, semiconductor devices as thyristors, integrated gate commutated thyristors, MOS-controlled thyristors and insulated gate bipolar transistors. History of HVDC technology. Electromechanical systems. The first long-distance transmission of electric power was demonstrated using direct current in 1882 at Meisbach, Munich. Power transmission, but only 1.5 kilowatts was transmitted. An early method of high-voltage DC transmission was developed by the Swiss engineer René Thurian. His method was put into practice by 1889 in Italy, by the Aquedotto de Ferrari Galliera company. This system used series-connected motor generator sets to increase the voltage. Each set was insulated from electrical ground and driven by insulated shafts from a prime mover. The transmission line was operated in a constant current mode, with up to 5,000 volts across each machine, some machines having double commutators to reduce the voltage on each commutator. This system transmitted 630 kilowatts at 14 kilovolts DC over a distance of 120 kilometers. The Montier's-Lyon system transmitted 8,600 kilowatts of hydroelectric power at a distance of 200 kilometers, including 10 kilometers of underground cable. This system used 8 series-connected generators with dual commutators for a total voltage of 150,000 volts between the positive and negative poles, and operated from c. 1906 until 1936. 15 Thury systems were in operation by 1913. Other Thury systems operating at up to 100 kV DC worked into the 1930s, but the rotating machinery required high maintenance and had high energy loss. Various other electromechanical devices were tested during the first half of the 20th century with little commercial success. One technique attempted for conversion of direct current from a high transmission voltage to lower utilization voltage was to charge series-connected batteries, then reconnect the batteries in parallel to serve distribution loads. While at least 2 commercial installations were tried around the turn of the 20th century, the technique was not generally useful owing to the limited capacity of batteries, difficulties in switching between series and parallel connections, and the inherent energy inefficiency of a battery charge-discharge cycle. Mercury Arc Valves. First proposed in 1914, the grid-controlled Mercury Arc Valve became available for power transmission during the period 1920 to 1940. Starting in 1932, General Electric tested mercury vapor valves in a 12 kV DC transmission line, which also served to convert 40 Hz generation to serve 60 Hz loads. At Mechanicville, New York, in 1941, a 60 MW plus or minus 200 kV, 115 km buried cable link was designed for the city of Berlin using mercury arc valves. But owing to the collapse of the German government in 1945, the project was never completed. The nominal justification for the project was that, during wartime, a buried cable would be less conspicuous as a bombing target. The equipment was moved to the Soviet Union and was put into service there as the Moscow Kashira HVDC system. The Moscow Kashira system and a 1954 connection by Uno Lams Group at ASEA between the mainland of Sweden and the island of Gotland marked the beginning of the modern era of HVDC transmission. Mercury arc valves require an external circuit to force the current to zero and thus turn off the valve. In HVDC applications, the AC power system itself provides the means of commutating the current to another valve in the converter. Consequently, converters built with mercury arc valves are known as line-commutated converters. LCCs require rotating synchronous machines in the AC systems to which they are connected, making power transmission into a passive load impossible. Mercury arc valves were common in systems designed up to 1972, the last mercury arc HVDC system having been put into service in stages between 1972 and 1977. Since then, all mercury arc systems have been either shut down or converted to use solid-state devices. The last HVDC system to use mercury arc valves was the inter-island HVDC link between the North and South Islands of New Zealand. which used them on one of its two poles. The Mercury Arc Valves were decommissioned on 1 August 2012, ahead of commissioning of replacement thyristor converters. Thyristor valves. Since 1977, new HVDC systems have used only solid-state devices, in most cases thyristor valves. Like Mercury Arc Valves, thyristors require connection to an external AC circuit in HVDC applications to turn them on and off. HVDC using thyristor valves is also known as line commutated converter (HVDC). Development of thyristor valves for HVDC began in the late 1960s. The first complete HVDC scheme based on thyristor valves was the Eel River Scheme in Canada, which was built by General Electric and went into service in 1972. On March 15, 1979, a 1,920 MW thyristor-based direct current connection between Cabora-Bassa and Johannesburg was energized. The conversion equipment was built in 1974 by Allgemeine Elektricitätsgesellschaft AG, and Brown, Bovary & Amp, CIE and Siemens were partners in the project. The late completion date the result of the Civil War. The transmission voltage of plus or minus 533 kV was the highest in the world at the time. Capacitor commutated converters. Line commutated converters have some limitations in the use for HVDC systems. This results from requiring the AC circuit to turn off the thyristor current and the need for a short period of reverse voltage to affect the turn-off. An attempt to address these limitations is the capacitor commutated converter, which has been used in a small number of HVDC systems. The CCC differs from a conventional HVDC system in that it has series capacitors inserted into the AC line connections, either on the primary or secondary side of the converter transformer. The series capacitors partially offset the commutating inductance of the converter and help to reduce fault currents. This also allows a smaller extinction angle to be used with a converter-inverter, reducing the need for reactive power support. However, CCC has remained only a niche application because of the advent of voltage source converters, which completely eliminate the need for an extinction time. Voltage source converters, widely used in motor drives since the 1980s. Voltage source converters started to appear in HVDC in 1997 with the experimental Hylsholm-Grängesberg project in Sweden. By the end of 2011, this technology had captured a significant proportion of the HVDC market. The development of higher-rated insulated gate bipolar transistors, gate turn-off thyristors and integrated gate commutated thyristors has made smaller HVDC systems economical. The manufacturer AB Group calls this concept HVDC Lite, while Siemens calls a similar concept HVDC Plus and Alstom call the product based upon this technology HVDC Maxine. They have extended the use of HVDC down to blocks as small as a few tens of megawatts and lines as short as a few score kilometers of overhead line. There are several different variants of VSC technology. Most installations built until 2012 use pulse width modulation in a circuit that is effectively an ultra-high voltage motor drive. Current installations, including HVDC Plus and HVDC Maxine, are based on variants of a converter called a modular multi-level converter. Multi-level converters have the advantage that they allow harmonic filtering equipment to be reduced or eliminated altogether. By way of comparison, AC harmonic filters of typical line commutated converter stations cover nearly half of the converter station area. With time, voltage source converter systems will probably replace replace all installed simple thyristor-based systems, including the highest DC power transmission applications. Advantages of HVDC over AC transmission. A long-distance point-to-point HVDC transmission scheme generally has lower overall investment cost and lower losses than an equivalent AC transmission scheme. HVDC conversion equipment at the terminal stations is costly, but the total DC transmission line costs over long distances are lower than AC line of the same distance. HVDC requires less conductor per unit distance than an AC line, as there is no need to support 3 phases and there is no skin effect. Depending on voltage level and construction details, HVDC transmission losses are quoted as about 3.5% per 1,000 kilometers, which are 30 to 40% less than with AC lines at the same voltage levels. This is because direct current transfers only active power and thus causes lower losses than alternating current, which transfers both active and reactive power. HVDC transmission may also be selected for other technical benefits. HVDC can transfer power between separate AC networks. HVDC power flow between separate AC systems can be automatically controlled to support either network during transient conditions, but without the risk that a major power system collapse in one network will lead to a collapse in the second. HVDC improves on system controllability, with at least one HVDC link embedded in an AC grid, in the deregulated environment. The controllability feature is particularly useful where control of energy trading is needed. The combined economic and technical benefits of HVDC transmission can make it a suitable choice for connecting electricity sources that are located far away from the main users. Specific applications where HVDC transmission technology provides benefits include undersea cables transmission schemes, endpoint-to-endpoint long-haul bulk power transmission without intermediate taps, usually to connect a remote generating plant to the main grid. For example, the Nelson River DC transmission system in Canada, increasing the capacity of an existing power grid in situations where additional wires are difficult or expensive to install. Power transmission and stabilization between unsynchronized AC networks, with the extreme example being an ability to transfer power between countries that use AC at different frequencies. Since such transfer can occur in either direction, it increases the stability of both networks by allowing them to draw on each other in emergencies and failures, stabilizing a predominantly AC power grid without increasing fault levels. Integration of renewable resources such as wind into the main transmission grid. HVDC overhead lines for onshore wind integration projects and HVDC cables for offshore projects have been proposed in North America and Europe for both technical and economic reasons. DC grids with multiple voltage source converters are one of the technical solutions for pooling offshore wind energy and transmitting it to load centers located far away onshore. Cable systems. Long undersea underground high-voltage cables have a high electrical capacitance compared with overhead transmission lines. Since the live conductors within the cable are surrounded by a relatively thin layer of insulation and a metal sheath, the geometry is that of a long coaxial capacitor. The total capacitance increases with the length of the cable. This capacitance is in a parallel circuit with the load, where alternating current is used for cable transmission. Additional current must flow in the cable to charge this cable capacitance. This extra current flow causes added energy loss via dissipation of heat in the conductors of the cable, raising its temperature. Additional energy losses also occur as a result of dielectric losses in the cable insulation. However, if direct current is used, the cable capacitance is charged only when the cable is first energized or if the voltage level changes. There is no additional current required. For a sufficiently long AC cable, the entire current carrying ability of the conductor would be needed to supply the charging current alone. This cable capacitance issue limits the length and power carrying ability of AC-powered cables. DC-powered cables are limited only by the temperature rise and Ohm's law. Although some leakage current flows through the dielectric insulator, this is small compared to the cable's rated current. Overhead line systems. The capacitive effect of long underground or undersea cables in AC transmission applications also applies to AC overhead lines, although to a much lesser extent. Nevertheless, for a long AC overhead transmission line, the current flowing just to charge the line capacitance can be significant, and this reduces the capability of the line to carry useful current to the load at the remote end. Another factor that reduces the useful current carrying ability of AC lines is the skin effect, which causes a non-uniform distribution of current over the cross-sectional area of the conductor. Transmission line conductors operating with direct current do not suffer from either of these constraints. Therefore, for the same conductor losses, a given conductor can carry more current to the load when operating with HVDC than AC. Finally, depending upon the environmental conditions and the performance of overhead line insulation operating with HVDC, it may be possible for a given transmission line to operate with a constant HVDC voltage that is approximately the same as the peak AC voltage for which it is designed and insulated. The power delivered in an AC system is defined by the root mean square of an AC voltage, but RMS is only about 71% of the peak voltage. Therefore, if the HVDC line can operate continuously with an HVDC voltage that is the same as the peak voltage of the AC equivalent line, then for a given current, the power transmission capability when operating with HVDC is approximately 40% higher than the capability when operating with AC. Asynchronous connections. Because HVDC allows power transmission between unsynchronized AC distribution systems, it can help increase system stability by preventing cascading failures from propagating from one part of a wider power transmission grid to another. Changes in load that would cause portions of an AC network to become unsynchronized and to separate would not similarly affect a DC link, and the power flow through the DC link would tend to stabilize the AC network. The magnitude and direction of power flow through a DC link can be directly controlled and changed as needed to support the AC networks at either end of the DC link. This has caused many power system operators to contemplate wider use of HVDC technology for its stability benefits alone. Disadvantages. The disadvantages of HVDC are in conversion, switching, control, availability, and maintenance. HVDC is less reliable and has lower availability than alternating current systems, mainly due to the extra conversion equipment. Single-pole systems have availability of about 98.5%, with about a third of the downtime unscheduled due to faults. Fault-tolerant bipole systems provide high availability for 50% of the link capacity, but availability of the full capacity is about 97% to 98%. The required converter stations are expensive and have limited overload capacity. At smaller transmission distances, the losses in the converter stations may be bigger than in an AC transmission line for the same distance. The cost of the converters may not be offset by reductions in line construction cost and lower line loss. Operating a HVDC scheme requires many spare parts to be kept, often exclusively for one system. As HVDC systems are less standardized than AC systems and technology changes faster, in contrast to AC systems, realizing multi-terminal systems is complex, as is expanding existing schemes to multi-terminal systems. Controlling power flow in a multi-terminal DC system requires good communication between all the terminals. Power flow must be actively regulated by the converter control system instead of relying on the inherent impedance and phase angle properties of an AC transmission line. Multi-terminal systems are rare. As of 2012, only 2 are in service. The Hydro-Quebec, New England transmission between Radisson, Sandy Pond and Nicolet, and the Sardinia mainland Italy link, which was modified in 1989 to also provide power to the island of Corsica. High-voltage DC circuit breaker. HVDC circuit breakers are difficult to build because some mechanism must be included in the circuit breaker to force current to zero. Otherwise, arcing and contact wear would be too great to allow reliable switching. In November 2012, AB announced development of the world's first HVDC circuit breaker. The AB breaker contains 4 switching elements, 2 mechanical and 2 semiconductor. Normally, power flows through the low-speed mechanical switch, the high-speed mechanical switch, and the low-voltage semiconductor switch. The last 2 switches are paralleled by the high-voltage semiconductor switch. Initially, all switches are closed, because the high-voltage semiconductor switch has much greater resistance than the mechanical switch plus the low-voltage semiconductor switch. Current flow through it is low. To disconnect, first the low-voltage semiconductor switch opens. This diverts the current through the high-voltage semiconductor switch. Because of its relatively high resistance, it begins heating very rapidly. Then the high-speed mechanical switch is open. Unlike the low-voltage semiconductor switch, which is capable of standing off only the voltage drop of the closed high-voltage semiconductor switch, this one is capable of standing off the full voltage. Because no current is flowing through this switch when it opens, it is not damaged by arcing. Then, the high-voltage semiconductor switch is opened. This actually cuts the power. However, it is not quite 100% off. A final low-speed mechanical switch disconnects the residual current. Costs of high-voltage DC transmission. Generally, providers of HVDC systems, such as Alstom, Siemens and AB, do not specify cost details of particular projects. It may be considered a commercial matter between the provider and the client. Costs vary widely depending on the specifics of the project. A detailed comparison of DC versus AC transmission costs may be required in situations where there is no clear technical advantage to DC, and economical reasoning alone drives the selection. However, some practitioners have provided some information. For an 8 GW 40 km link laid under the English Channel, the following are approximate primary equipment costs for a 2000 MW 500 kV bipolar conventional HVDC link converter stations. £110 million. Subsea cable plus installation. £1 million per kilometre. So for an 8 GW capacity between England and France in 4 links, little is left over from £750 million for the installed works. Add another £200, £300 m for the other works depending on additional onshore works required. An April 2010 announcement for a 2000 MW 64 km line between Spain and France is estimated at €700 million. This includes the cost of a tunnel through the Pyrenees.